So now let's look at how do we solve when we have a nonlinear, or how do we set up a nonlinear model? Again, solving them you've done, but this is just how to actually set up a nonlinear model. Um, so going back to exponential growth is where the rate of change of your population is proportional to the size of the population. And so therefore your growth rate is the rate of change divided by the size. Well, that's great, except what if that rate of change isn't constant? So in exponential growth problems, we assume the rate of change is constant. But what if it's not constant? What if it's actually to a function of your population size? In other words, your rate of change is the population size times this rate of this function of where it's changing. We want to look at what this looks like and what this becomes. And so this gets us what we call a logistic growth model. And this is where the environment can only sustain a limited number of individuals. We call that M. It's called your carrying capacity, is another way to think of it. So if you think about a petri dish, it only has so much food. The whole idea of the petri dish is it provides food for the organisms that are growing in it. At some point, those organisms no longer can sustain it. There's no longer any food left in the petri dish. So at some point, they run out of food, they run out of space because they've taken up most of the space as a petri dish. So then it starts to die off because you can't get that. So if you go beyond the carrying capacity, you're going to die off. If you are you won't grow anymore if you're below the carrying capacity. So the idea is, what does this look like? So let's look at a function. And let's say that at this carrying capacity, therefore, your f of your carrying capacity, m, is equal to 0 because there's going to be no growth. So once you hit that carrying capacity, if you actually got the size of your population is the carrying capacity, you're not going to grow at all. So there's no growth there. All right, so let's think about what this might look like and what it would be. Let's talk about at the start of time, whatever your time period starts, you're going to have some growth. Let's call that, I don't know, give it a name. Let's call it R. All right, so let's think about, we've got these two pieces here, these 2 points at time 0, and this is your function. At time 0, you're going to have a value of R. And at time M, maybe not, I shouldn't call it time. This is actually not time. This is population size. So, sorry, not time, but population size. At time M, you're going to be 0. And so you got to think about, how do we get from R, from time 0, 0R to M0? And there's different ways you could do this. One way is to come straight line. So you could go linearly to there. You could also go a curve that comes up and goes down to it like that. Or you could have one where you have a curve that starts slower and then, or starts fast and then slows down. So we could have all these different ones to look at. We are going to go ahead and assume it's the linear because it's easier. So we're going to go ahead and assume that the linear one is the one we want. So if that's the one we're going to have, then f of p is going to equal, well, the equation of a line, which is slope times your variable plus your y-intercept. Okay, cool. So let's find the slope. Remember, the slope is just the point, is just between 2 points, is just the difference in the y's over the difference in the x's. So my y's are difference is m minus r. Sorry, not m. Sorry. 0 minus r. Over top of, because this height is 0 and this height is r, and then over top of m minus 0. So we get that it's minus r over m. Okay. B is your starting point, your y-intercept. So B, 0b, is going to be 0r, because that's where you started. All right, so now we can get our equation. F of P is going to equal my slope plus my r and my y-intercept. So r minus m, r over m times p. So there is your function. And from that, we can then get the differential equation. So then now the differential equation, and we'll go to a new page on this. Now my differential equation would be that dp dt is going to equal my, remember it's p times f of p. This is going to be equal to p times my f of p, which we just came up with, is r minus r over m times p. So we end up with this wonderful equation. To make life a little bit easier, just for doing some of the derivation, I'm going to go ahead and let r equal a, and I'm going to let r over k, or r over m, sorry, equal, we'll call it b. And so therefore, my logistic equation now becomes dp dt is equal to p times a minus b times p. It just makes life a little bit easier for us to do the work. And this is known as a logistic equation. And we can now solve this. The solution to this is the logistic function, and the graph is called the logistic curve. And we can actually go ahead and graph up one. So I'm going to go ahead and go into a differential equation drawing that draws slope fields. So we're going to go get our slope field. I happen to like the Buffton University site one. And we're going to go ahead and put this in. We're going to put in, it's my independent variable, which is in this case, x times a minus b. Well, let's call a, I don't know, let's call a 5 and b1 times my, actually, sorry, it's not my independent variable, it's my dependent variable. And so we have this equation now. So let's just say that this is what we have. I think I need a multiplication symbol here. And let's just put one here just to make sure. It's not graphing up. So maybe it did graph. Y times and there we have it. And I'm going to change this window a little bit. Maybe that's my problem. I can't see enough of the window. So let's let our x's go to maybe 10. And maybe our y will go up to 10. No, maybe 100. or 1,000 or 10,000. Oops, it's too high. There we go. 10 was right. I don't know why I didn't stop there. Okay, so here's our graph. And you can see from this that if you were to come up and come along, you're going to notice you're going to have an asymptote here. And in fact, this is an autonomous system because it doesn't involve the independent variable. It's just a dependent variable. So this is autonomous. So this is an autonomous equation. And notice we do have a horizontal asymptote in here. In fact, if I were to plot one up, let's pick a starting point. You can see it's going to come along. We're going to start it here. We're going to come up, and then we're going to level off. And so this gets you to the idea of the carrying capacity. All right. The solution to a logistic equation is, well, let's talk about how we would do this. Well, one of the things you notice is this is separable. So we could, in fact, solve this by doing a separable notation, separable solution. So we'll start with our differential equation, and then we will solve this differential equation. So the solving this, it is a separable equation. You have 1 over p times a minus b times p dp is equal to dt. And then we just need to take the integral of both sides. And the integral of p, 1 over p times a minus bp is negative 1 over a natural log of a minus b times p over top of p. And of course, the integral of t, dt is just t, so t plus c. And then we just need to solve this for p. So the first thing I'd probably do is take this negative 1 over a to the other side, so negative at plus c. And then get rid of the natural log by raising e to both sides. And so you have a minus b times p over p is equal to c e to the negative at. Oh, wait, I think I wasn't supposed to have this negative sign here. I apologize. Sorry. Oh, no, I know what I did. I did want that negative sign there. But what I want to do, instead of taking the negative sign over to this side, I'm going to leave it on this side. And I'm going to take it up to this negative power up there. Makes life a little bit nicer just to not have that negative sign. What that does for us is it actually flips this one over top, upside down. So this would be p over a minus b times p. So that being the case, we will now solve the rest of this for p. First, multiply both sides by the denominator. Oh, forgot to bring my c down. All right, so then what we have is we would then, let's see, p plus b c e to the at times p is equal to a c e to the at. Multiplying that through and taking it over to this side. Take your p out. And then p is going to be a times c e to the AT over top of 1 plus BC e to the AT. And so there's your answer. We don't particularly like having this e to the AT all over the place. So if I divide through by e to the negative AT, I'll get rid of it from the top. That will put 1 down here and gets rid of that 1 there. So this is just another way to look at it, just a different way. It's the same idea. Remember, this was an initial condition. So P of 0 was R, we'll call that P0. We'll tell that whatever you start your population at. I will mention that A over B does not equal P0. And if it did, then we would have some problems and things would cancel out that we don't want to cancel out. All right, so there's our equation, and there's our logistic function, and we already saw the logistic curve. Another equation that we can also work with is what we call chemical equation. Oh, I should mention, by the way, on this, that as P goes to infinity, this thing will go to A over B. So, because you can see that as T goes to infinity, the e to the negative AT goes to 0. So we have AC over BC, which is going to give me A over B. And that's another reason why we can't let A over B equal P0, because that is your carrying capacity. And if you're already at the carrying capacity, then you can't go anywhere. So that's why we're not let that happen. All right. And if you happen to have, I should mention also one more thing, sorry, is if you have a harvesting factor, this is assuming there's no harvesting going on. If you have a harvesting factor, then you have more things that go on, and it actually would change out what's happening with this. And you would not hit the carrying capacity because you would be harvesting some. So it does change a little bit. We're now going to look at chemical reactions. Suppose you have A grams of chemical A and B grams of chemical B, and M parts of A and N parts of B form C when combined. And so that's how we do chemical reactions. We actually put two chemicals together in different parts, and they react in such a way that they'll form a new compound. We call it C. X of T is the amount of grams of chemical C formed at time T. Okay. And what we want to do is we want to come up with what this differential equation would look like. So the number of grams of A remaining at time T would be, well, you started with A and you took some out. You took some out that made your C. And the ratio you took them out is M over M plus N. And the reason that is that again, you take M of A to make some of it, and you take N of B to make some of it, and you get this ratio of the combination of these. And then the M of the number of grams of B remaining at time T would be B minus N over M plus N of X of T. And same kind of thing is N's how much you had to take. M plus N is the combination. So if you have M, and let's say you have 5 grams of A and 2 grams of B. So you'd have 5 over 7. So 5/7 of it would go away because 5/7 of it made it X. And 2/7 of it would go to making B, making C. So that's why this works this way. And the rate will form a product of A and B that's not transformed. So this is how much is left. So this means some of it went away, and this fraction went away because some of it went to make your new thing, but some of it's left. And so we can look at how much is left of A and how much is left of B. And the product of those will tell you what is left to be transferred. And it's proportional, so that's why we have that proportionality constant in there. And this kind of shows you how it puts together. And so what we want to do is kind of figure out what this is. And so two chemicals, let's say A and B, are combined to form a chemical C. The rate or velocity of reaction is proportional to the product of the instantaneous amount of A and B not converted to C. Initially, there are 100 grams of A and 50 grams of B, and for each gram of B, 2 grams of A is used. It is observed that 10 grams of C is formed in 5 minutes. So how much is formed in 20 minutes? And what is the limiting amount of C after a long time? How much of the chemicals A and B remain after a long time? That's kind of the question we're asking. So let's see how we go about doing this and what this looks like. So I don't really use the formula that much, and that's why I kind of didn't spend a lot of time on it, is that I want to look at how to do this in general, and that's what it's a better way to look at it. So first off, we have 100 grams of the one chemical. So remember, there's 100 grams of A and 50 grams of B. So we're going to call M 100 grams and N 50 grams. And you can call them anything you want. I don't really care. I just decided to call them this. And we're told that there are 2 grams of A are used for 1 gram of B. So for every gram of B, we use 2 grams of A. All right, so we have that information also. X of T, give it a name, is the number of grams of C present at time T. You obviously at the start, you don't have any of C. So at the start, you have nothing of C. We also happen to know that after 5 minutes, there's 10 grams of C. So we're told that in the problem. Okay. So again, let's say we have A, little a is the number of grams of A. And little b is the number of grams of B. Okay. Now for every gram of B, you get 2 grams of A. So if that's the case, if you have 1 gram of B, you get 2 grams of A. If you have 2 grams of B, you'll get 4 grams of A. If you have 3 grams of B, you'll have 6 grams of A. If you have X or B grams of B, you'll get 2B grams of A. So that tells me that A is equal to 2B. All right. Also, you can't get the amount that's going to be formed of C can't exceed A and B together. So in fact, A plus B has to give you X. So that means that since we now know that A is equal to 2B, 2B plus B is equal to X. So 3B is equal to X. So now let's look at the amount of A remaining. So let's look at the amount of A remaining at time T. All right, so that would be, well, we started with 100 grams of it. We are gonna, for every, we're gonna have 2 grams go away, and there's gonna be 3 grams total, so it's 2/3 of what we started with, okay? And then we also can look at the amount of, so think of this is that you have if you have 3 grams of something, 2/3 of it went to A, went away from A. So there's 1/3 left of that, basically, of A, because 2/3 is gone. The amount of B remaining at time T, well, that will be how much we started with. We started with 50 grams. And for every gram of B, there's gonna be 3 grams of X. So you get a 1/3 of it going away. Think of it that way. So now we know that we can look at dx of t, the rate of change, is proportional. We were told that in the problem that the rate of change was proportional to the product of the instantaneous amount of A and B not converted. So dx dt is proportional to the amount of A not converted and the amount of B not converted. And if you think about this, this makes sense because as you get less and less A, you're not going to have a very fast reaction. And if you get less and less B, you're not going to get a very fast reaction. But when they have a lot of both, you're going to have a much faster reaction. Proportionality means that we have a proportionality constant. So we'll throw that in. And here is your equation. This is, in fact, separable. And so you can actually go ahead and separate it out and solve it. I would probably do a little bit of simplifying here. One of the things I noticed is I don't like fractions. So I would pull 2/3 out. And when I pull 2/3 out, that means I'm going to get 150 minus X here. Because I'm taking 2/3 out. So think of it as 2/3 of 100 is 150. And then you're going to take 2/3 out of this one. Or actually, I'm going to take 1/3 out of this one. And 1/3 of this one is going to give me 150 minus X also. So we end up with 2/9 times your proportionality constant times 150 minus X squared. And so now we can actually go ahead and solve this. This is now separable. And so you can solve this equation. I'll let you do that once you actually take the separate it and find the solution. Remember that you were told that the amount after 5 minutes of C is 10. That will allow you to find that K, and then your 0 will allow you to find your constant.